Side channel attacks are perhaps the most successful attacks to modern cryptographic systems for two main reasons. First, they target the weakness of the implementation of the crypto algorithms, not the algorithms themselves. Therefore, a mathematically sound algorithms can become vulnerable against side channel attacks. Second, these attacks are non-invasive, passive, and most of the time will not leave any trace of attack. They use the signals leaked from side channels during system's normal execution to reveal the secret information, so it is hard to detect and catch such attacks. This week, we will study side channel attacks. We will start with what are side channels, why they may leak information, how attackers can take advantages of these vulnerabilities to launch side channel attacks. We will discuss in details on four representative attacks: cache attacks, power analysis, including both simple power analysis and differential power analysis, timing attacks, and scan chain attacks. Of course, we will also talk about the countermeasures from software, hardware, and algorithms. Some background on electrical engineering will be helpful to understand the mechanisms of information leak through different types of side channels. To follow the example we are going to use, you need a good understanding of the concept of modular exponentiation and Montgomery reduction that we have learned last week. Some basics on assembling programming will be helpful for a couple of examples, and some entry-level knowledge about the cache and memory structure are needed too. I will try to cover this background as needed during the lecture. Side channel attacks normally have two phases, a measuring phase and a data analysis phase. During the first phase, the attacker will monitor the system's physical characteristics when the system is running at the normal mode. These physical features can be power consumption, current, timing or delay, electromagnetic information, acoustic information, optical information, etc. Then, during the second phase, the attacker will perform data analysis on the collected side channel data to determine the on-chip secret information of interest. Normally, further measurement will be collected to confirm the deduced secret information. Side channel attacks are non-invasive because they do not require to open up the chip. Some of the attacks do not need to have physical access to the chip either. For example, the EM attacks and acoustic attacks. Side channel attacks are also passive, as the attacker will be monitoring the normal operation of the chip. However, there is the trend of combining side channel attack with active attacks to improve the efficiency and effectiveness of the attack. For example, by doing input control, the attacker can put the chip in the normal operation with his input data, and the attacker can use fault injection techniques to force the system to run at some abnormal conditions. This will help the attacker to collect more valuable side channel information that are not easily available through a passive monitoring process. There are many side channels that can be utilized by the attackers: the power consumption and execution time during the normal operation, the electromagnetic information, the optical and acoustic emission, as well as the system's output signals. Next, we'll briefly discuss each of these. First, the power and current side channel is perhaps the side channel that has been studied extensively in the past 20 years or so. Chip's power consumption mainly comes from three sources: the dynamic power that is needed to charge and discharge the capacitance, the leakage current that will occur even when the system is idle, and short circuits and others. Information may leak from dynamic power consumption because it is proportional to the effective capacitance of the switching activity. A switching happens when we change a logical 0 to a logical 1 or a logical 1 to a 0. This will incur higher power consumption than the case when the logical value remains at 0 or 1. On the other hand, leakage current may leak information about the system because the leakage current of a logical device is related to the input value to this device. For example, for this 2-input NAND gate, the leakage current when both input signals are 1 is about 454 nanoamp, about 12 times higher than the leakage when input vector is 0 and 0. Naturally, timing or delay is related to the execution time of an operation. The execution time of different operations may be different. The execution time of the same operation with different operands or under different conditions may also be different. This will give attacker some insight about the system's internal information. For example, the control flow will leak data when different branches execute very different instructions. Take this if-else statement for example. It will take longer time to perform the operation x equal to c minus d in the false branch than the operation x equal to 8 in the true branch. If the attacker can manage to measure the execution of this portion of the code, whether A and B have the same value can be deduced. The data dependency nature of many operations can also leak information. Consider a very simple multiplication operation x times y and assign the product to x. The execution time when y equal to a number such as 190 will be very different, in particular will be much longer than the case when y equal to 0, y equal to 1, or y equal to 64. In the last case, because 64 is 2 to the power 6, so this multiplication normally is implemented by a logical shift, which takes much shorter time. In addition, monitoring execution time can also reveal whether cache misses and pipeline stores have happened. This may also leak the memory content, in particularly the cache memory content. EM emissions originate from the acceleration of charges in a conductor or antennas. In the near field range, which is about 2 wavelengths from the antenna, the electric and magnetic fields are dominated by EM waves. However, their intensity drops quickly as the distance gets further away. Why data may leak from EM emissions? This is because they can modulate other on-chip signals through near-field inductive and capacitive couplings. This makes it possible to use the EM traces as set-channel signals to discover operations inside the chip. Optical emissions come from the movement of hard carriers, including both electrons and holes. When they move in a fat channel, they can cause a visible or infrared light emission. This can be captured by charge-coupled device cameras and used to help IC testing and debugging. If this information about the circuit can be used for testing and debugging, it is also possible for an attacker to use the same information to extract information about the system. This type of attack can be used to detect the data from all kinds of hardware devices, from microcontrollers and smart cards to FPGAs and ASICs. Acoustic information has been used to attack hardware systems for several decades. When a key is entered from the keyboard, or when certain system components are running, sound might be captured. For example, in the 1950s, British intelligence agents determined the starting position of the Egyptian encryption machine by listening to the resetting of the key wells. In old spy movies, we have seen phone numbers leaked from the dial tone. Text printed on the uncertain dot matrix printers can also be detected from the acoustic side channel information. The reason for information leak from acoustic channel is fairly straightforward. The acoustic traces of different key being hit on the keyboard are different. Microphones can capture this and other sound information during systems components during execution. For instance, it was reported that on a home-built PC with RSA encryption implemented, when a microphone is placed close by, it can capture the acoustic information to tell when the RSA encryption algorithm is running. Furthermore, the runs of the RSA with different key values give different acoustic traces. It is speculated that the acoustic emission is the result of the piezoelectric properties of the ceramic capacitors used on the motherboard of this system. This is related to the power and the current draw on the chip. Finally, we talk about the scan chain side channel. This is another perfect example to show how design features that are introduced for good intention can make the system vulnerable. This figure shows a core and a test and the scan chain built to facilitate the testing. The original 5 D flip-flops have been modified and connected by this chain through the Q port of the flip-flop to the input of the next flip-flop. A testing control signal, which is called the TC here, controls the input to the D flip-flop. When TC equal to 0, the signal coming from the core and the test will be used to keep the system running at the normal mode. However, when we change the TC value to 1, the system changes to the testing mode, and the testing input vector will come from the scanning port and forward to each of the flip-flops through this scan chain. For example, if we want to test the system with state information 0, 0, 1, 1, 1 from left to right, we can push the input vector 1, 1, 1, 0, 0, 1 bit at each clock cycle from the scan-in input port. And this, at the end, these values will go through the scan chain to the designated flip-flops. For example, the first bit 1 will travel through the first scan flip-flop to the second one on the second clock cycle, and the third one and the fourth one, and eventually reach the last flip-flop. After that, we can change the test control signal to 0 to let the system run at the normal mode. And then the result will be written back to the flip-flop. Now we change the test control signal back to 1 for the testing mode, and then we can get the result from each flip-flop from the scan-out signal. This is one of the most important inventions in design for test. It allows the tester to test any system state at any time. However, these scan flip-flops can be turned into a side channel that will leak the system state information directly from the scan-out signals when the attacker set the TC value to be 1 for the testing mode.